Right, here's our last example in section 15.5 where we've been finding the area in between two curves. Remember that finding the area in between two curves is really integrating top minus bottom from A to B. So if you look at this problem, this is more of an application problem. It says a company is considering a new manufacturing process in one of its plants. The new process provides substantial initial savings, with the savings declining with time in years according to the rate of savings function. So this is the rate at which the savings is changing. This is the derivative, right? And so it says here that the savings goes up and then it kind of starts to decline. So it looks something like this, right? It says where S prime of t is in thousands of dollars per year. At the same time, the cost of operating this new process increases with time in years according to the rate of cost function. So S is the rate at which we're saving, but C is the rate at which it's costing us money in thousands of dollars per year. And in that one, it looks like the cost is kind of going to go up, right? So at some point, your savings is higher than your cost, but at the other point, there's a point in time where the cost ends up going higher than your savings, right? Your cost is increasing more than your savings is increasing. And so that's the point that you want to consider doing something else, right? And so for part A, it says how many years will the company realize savings? Well, what we want to do is we want to figure out what this time is. At t equals what time do we want to stop using this new process and maybe think of a different process that's going to save us money and not cost us more than it's going to save us? So we want to figure out where those two functions cross, right? And so we want to figure out where their intersection point is. So let's take those two functions, s prime and c prime, and set them equal to each other. My s prime was the function 100 minus t squared. My c prime was my t squared plus 14 over 3t. You notice that it's a quadratic function, so I'm going to move every term to the same side and set it equal to 0. I also noticed once I moved everything to the same side that I had a little bit of a fraction in there. I have a 14 over 3. And it's a little bit harder to solve quadratics, whether I'm doing factoring or quadratic formula, if there's fractions. So the first thing I'm going to do before I start to solve is I'm going to actually go through and get rid of the fractions by multiplying every single term by the common denominator, in this case, a 3. I'm going to multiply my first term by 3, my second term by 3, my third term by 3, and my fourth term by 3. I'm going to go ahead and distribute 3 to everything. What that's going to do, it's going to allow me to take all of my terms and make sure that there's no more fractions. So now I have this quadratic equation, 6t squared plus 14t minus 300, and I want to go ahead and try to solve it. I'm going to first try to solve by factoring. I noticed that there is a GCF of a 2, so I'm going to take out a 2. Then I'm going to factor the leftover trinomial, and I'm going to use bottoms up. You can use whatever method you've learned for factoring a quadratic equation that has a leading coefficient other than 1. When I ended up factoring it, I factored that GCF of a 2, and then I have two other factors, 3t plus 25, and then I have a t minus 6. I'm going to take each of these factors, I'm going to set it equal to 0, and I ended up getting, on this one, t equals negative 25 over 3. But if you remember, t in the problem really represented time in years. And it wouldn't really make any sense to say t equals negative time, because you can't really go back in time. When I set my other factor equal to 0 and I solve, I ended up getting t equals 6. So what that means is these two functions, the cost function and the savings function, intersect, they're the same, at t equals 6. That's 6 years since I started this new process. So that's the time where the cost is going to go higher than the actual savings. So that's when we're going to realize our savings, and we're going to have to make sure that we reanalyze what we're going to do. Part B of this equation, or this question, says, what will the net total savings be during this period? So I want to know what my total savings is. I know the rate at which I'm saving, and I know the rate at which it's costing me money, but I don't have the actual savings. That's my original function. But if we know the derivative, the rate at which I'm saving and the rate at which it's costing me, I can integrate and find the antiderivative. That'll be the actual savings I have over that period of time. What we're really doing is we're finding the area in between my cost function and my savings function, right? Where I'm going to go ahead and start at t equals 0, and I'm going to end at that t equals 6, because I want to know how much I'm saving in that time, from the beginning all the way to year 6. So let's set up an integral from 0 to 6 of my savings, my top, minus my cost, my bottom. Remember, if I'm finding the area in between two curves, I want top minus bottom. Let's plug in our functions. Let's distribute that negative and combine like terms. And so now I can find the area underneath the curve, between these two curves I should say, from 0 to 6. What that's going to do is it's going to give me the antiderivative, which is the actual savings compared to the actual cost over these 6 years. Let's integrate. I ended up getting negative 2t cubed over 3 minus 14 over 3t squared over 2 plus 100t, and we want to evaluate it from 0 to 6. That means I'm going to plug in my upper limit, my 6, I'm going to plug in my lower limit, my 0, and then I'm going to subtract those two. Putting it in my calculator, I ended up getting 372. Remember, when we're integrating our derivative, our rate at which the savings, and rate at which our cost is changing actually gives me the actual savings and the actual cost. So I can find the total cost over those period of 6 years. I ended up getting 372, which remember was in thousands of dollars, right? If I go back, they were in thousands of dollars per year. So when we say 372, this really means over that 6-year period, our total savings was $372,000. It was saving us more than it cost us until I hit that 6-year point. So I need to make sure that we do something different after those 6 years. But from 0 to 6 years, it ended up actually saving me a total of $372,000. We got that by integrating our derivative, by finding the area in between the cost function and the savings function.